quiz.
A pleasant morning, everyone, and a very warm welcome to the day 4 of Qiskit Fall Fest 2025, proudly hosted by Rgukt Srikakulam and sponsored by IBM Quantum. Over the past 3 days, we have embarked on a phenomenal journey, exploring the depths of quantum circuits, agentic AI, and Qiskit's real world applications through insightful lectures, interactive workshops, and mind opening discussions. Each day has been a step forward in transforming curiosity into capability. And guess what? The momentum hasn't stopped here. Because today, we have an absolutely power packed lineup. A day that promises not only to engage your intellect, but to ignite your imagination. Let me walk you through the schedule of day 4 for a while. Initially, we'll be kickstarting our morning with Mr. Abhijith Tej, Knowledge Associate, CDAC Hyderabad, who will lead an immersive hands on demonstration of the Indigenous Quantum Computer Simulator Toolkit QSIM, a brilliant opportunity to witness India's own quantum simulation innovation in action. Followed by diving into the fascinating realm of quantum algorithms from basics to advanced, guided by Mr. Soumya Ranjan Swain, Gen AI leader and IBM Quantum Ambassador. A session designed to decode the logic behind the magic of quantum computation. And then we will be honored to host Mr. Sai Shankar, IBM quantum research scientist, for a special virtual guest lecture. And we'll be getting ready to gain profound insights directly from one of the finest minds in quantum research. And to wrap up the day, we'll be bracing ourselves for a hands on workshop on Qiskit conducted by Dr. Gnan Yalla, CTO Datatech.ai, and quantum machine learning researcher. An afternoon dedicated to complete experimentation, collaboration, and practical exploration. So, dear participants and everyone, whether you're joining us in person or virtually, let's keep this same enthusiasm alive that has defined the last 3 days of the fest. Because learning in the quantum world is not a destination, it's an evolution. So, it's time to begin day 4 with curiosity, creativity, and the quantum spirit that defines this fest. And to do so, we move on to one of the most exciting and awaited sessions of Qiskit Fall Fest 2025, a session that brings innovation, technology, and Indian excellence together on one platform. It gives us an immense pride to welcome our distinguished speaker, Mr. Abhijith Tej Vadeboina, Knowledge Associate at CDAC Hyderabad, and most importantly, a proud alumnus of RGUKT. Mr. Abhijit began his academic journey with his PUC at RGUKT Basar, where he laid the foundation for his passion for technology and research. He then pursued his Bachelor's of Technology in Electronics and Communication Engineering from the Institute of Aeronautical Engineering, followed by a master's degree in quantum technology from the prestigious Indian Institute of Space Science and Technology. With a deep interest in cutting edge technologies, he has also worked with the research and innovation labs at Tata Consultancy Services, TCS, contributing to advancements in quantum communication, and currently serves at CDAC Hyderabad, where his work focuses on quantum computing and quantum algorithms. Today, he is here to guide us through an engaging and hands on session on Indigenous Quantum Computer Simulator Toolkit, QSIM. So get ready to explore the world of quantum simulation in action. Let's put our hands together and give a warm, enthusiastic welcome to Mr. Abhijit Tej Vadeboina as we invite him onto the dais to lead the exciting session.
Hello all. Am I audible? Yes. Good morning, everyone. Thank you. Thank you very much, Ajiketi Srikakulam, for inviting me here. And thank you for the wonderful introduction also. You, sure, sure. It's actually a great time to learn quantum technology. You people are from, yeah, second year BTech, third year BTech, fourth year BTechs. It is a bright time because in next 5 years or 10 years, many of the quantum software engineers are coming from India. So it's a great opportunity to learn quantum right now. So I'll start my session with a brief introduction into quantum technologies, how it evolved, how it gives you an advancement over classical technologies, and then I'll show you about a quantum simulator QSIM, which is developed by IISc Bangalore, IIT Roorkee, and CDAC. So let us start the session. Are you excited? Yes, yes, great. So is my screen visible? Presentation screen? Just a moment. So we know, like if you all are using laptops, you all are using mobile phones, etc. So from where did this all start? It started somewhere in 1940s and 1950s, and with the advent of vacuum tubes, and then transistors, then integrated circuits, then microprocessors, then very large scale integrated circuits, etc. So we are all in this ultra large scale integration circuits, very large scale integration circuits, etc. Billions and billions of transistors are in single 1 inch chip, which we are using in our mobile phones right now, or else in our laptops right now. See, this is the advance of the technology from the last 40, 50 years. What next? See, billions of transistors are being inserted onto a 1 inch chip, which means the size of individual transistor is getting reduced. So somewhere, if you reduce the transistor size, you have to enter into the quantum era, which is around nanometer dimension or Armstrong dimension, where quantum effects will come into picture. So the next set of computing is quantum computing. So these are all classical case examples of classical computers. Laptops are there, mobile phones are there. Then we all know about Moore's law, what he predicted: for every 2 years or for every 18 months, number of transistors on a single chip will get doubled. And somehow, because the transistor size gets doubled, the transistors get doubled, transistor size reduces. And because of the reduction of the transistor size, so somewhere we have to go into the quantum domain. So that is the final part. So we have to be ready for this new approach. And we have already found out some significant limitations of our daily based laptops. Yes, we are doing a lot of work on it. Whole world is running on these laptops, computers, internet, etc. But there are limitations. What are those limitations? Binary processing. Classical computers act as switches, which means they can be either 0 or 1, but not both. So either it is on switch or it is an off switch. There are scalability issues, and then inefficiency in executing certain algorithms. It takes millions of years for even the hardest, strongest of the supercomputers to solve certain problems, which can be solved by using quantum computers. So simulation of quantum systems is also a difficult case if we use classical systems. Then there is a high energy consumption. So that is why people are thinking about quantum technology. So what does quantum technology include? It is a multidisciplinary field. It is not only a computing, it is not a single code. It is wholly different architecture. You need people from different disciplines in order to develop something as specific and as technologically hard as a quantum chip or a quantum computer. So what happens is quantum technology is a multidisciplinary field. It has physics, it has computer science, it has electronics, it has electrical engineering, vacuum systems, and then you need dilution chambers. You have to understand how to cool down the temperatures. You have to understand about vacuum. So basically, you're playing with atoms. The whole you're making the nature as a computer itself. That is the frank idea behind quantum technologies. What are main technological core areas that are in quantum technology? Quantum computing and quantum simulations. So quantum computing, this involves quantum information theory, quantum developing new quantum algorithms which can solve our daily life problems. Then quantum communications. In by using quantum mechanical principles, we can develop secure communications without even using cryptographic algorithms, because nature gives you that secrecy. nature itself hides your information. So that kind of technical potential is available in quantum communication, quantum sensing, and quantum metrology. uh, Even the sensors which we use right now, they have a limit. They have a classical noise limit. If you want to go beyond that, you have to use quantum sensors. Then there is a separate set on quantum materials and quantum devices, which we have to develop in order to enhance the quantum technology power. So what does quantum technology promise you? An exponential increase in computation speed, the ability to break some cryptographic systems, then high degree of information security guaranteed by the laws of physics, exquisite, sensitive, and accurate measurements, and improved atomic clocks. So these are some things, and we can also improve financial markets, drug design, space applications, genetics, etc. So this basically gives you what all the areas that quantum technology can affect. So how did it all begin? So there is always people are talking about quantum computation. Yesterday or day before yesterday, if you follow the news, Google has claimed that its algorithm has worked 13,000 times better in a practical scenario than the world's fastest supercomputer. They have practically proven the quantum advantage 2 days back. Did you follow the news? Yes, yes. So quantum technology is the reality right now. So how did it all begin? So a very basic introduction. 19th century, when people thought classical physics and electromagnetic theory, it explained everything. Everything is good. So scientists thought, yeah, only precise measurements are left, no new science is there. But the nature said no. Scientists observed abnormalities in black body radiations, Rutherford atomic model of atoms, and everything. Some classical calculations failed to quantify the phenomena that is happening around in nature. And then that is how we thought that nature doesn't behave classically. And then the experiments like photoelectric effects and atomic models like Bohr's atomic model and all this led to the quantum theory. Finally, we came to the conclusion that subatomic particles behave differently when compared to the objects through which they are made of. Dual nature of matter was observed. Scientists observe peculiar behavior not only in wave particle duality, but also in phenomena like quantum tunneling, quantum entanglement, etc. So, all these ideas, all these principles famously led to this quotation called nature is quantum. So, if you have to simulate nature, you have to develop quantum computers. This is said by the great scientist Richard Feynman. So, this is how the idea of quantum computing was developed. So, what is quantum computing? It is a type of non classical computing based on the quantum state of subatomic particles. The behavior is governed by the laws of quantum mechanics. Quantum computing is fundamentally different from classical computers, which operate using binary bits, which is a switch, either a 0 or 1. This means the bits are either 0 or 1, true, false, positive, negative, etc. However, in quantum computing, we refer to the bit as qubits. You all know that we refer to the bit as qubits. Unlike strictly binary bits of classical computing, qubits can strangely represent a range of values. It can be in a superposition of 0 and 1 at the same time. That gives you more processing power. So, this is the main advantage of quantum computing. Superposition is what gives quantum computers the speed and parallelism. Further, qubits can be linked with other qubits in a process called very peculiar and strange non-local process called entanglement. When combined with superposition, quantum computers can process a massive number of possible outcomes. The number of high quality qubits necessary to make a viable quantum computer will be dependent on the problem. The ability of a quantum computer to outperform a classical computer is called quantum supremacy. See, that is what, if you search in Google and say, if you go to any browser and search for quantum supremacy, many companies recently they are claiming that their quantum machines are performing better than the fastest classical ones. So this kind of quantum supremacy will be reality. What are the basic principles of quantum in a generic language? So why quantum is different is because it has features like superposition, quantum tunneling, quantum entanglement. So superposition states that a physical system may be in one of the many general configurations. Then the most general state is a combination of all these possibilities. So it can be 0, it can be 1, it can be anything in between all this range. Quantum tunneling is a quantum mechanical phenomena where particle passes through the potential barrier instead of jumping through it. Quantum entanglement is a phenomena where two quantum states or more objects have to be described with reference to each other, even if they are spatially apart. If one quantum state is with me here, quantum qubit is with me here, and I have entangled some qubits, for example, two qubits. If one is with me here and one is in my office at Hyderabad, even though I change it here, the qubit which is in my office at Hyderabad changes instantaneously. So this kind of non-local interaction happens only at the quantum level. So how did quantum computing, the idea and the thought of quantum computing evolve? So in 1980s and all, Richard Feynman proposed this idea that in order to simulate nature, you have to develop quantum computers because everything in nature follows an exponential phenomena. If you observe anything around nature, nitrogen cycle, if you observe something like for a very small example, take some lake or something, the weed or grass that will grow in the lake will double every day. So that follows this exponential nature. The nature is exponential. Nature is quantum. So this kind of phenomena can only be simulated using quantum computers. Then in 1985 and all, David Deutsch developed quantum Turing machine. 1994, Peter Shaw came up with the quantum Shaw's algorithm, which, if an efficient quantum computer is there, it can break classical RSA or elliptical cryptographic systems. Then Grover develops Grover search algorithms, which produce big O of root n complexity. So it halves the by root n, it reduces the complexity. So this is a general history. So basically, we are talking about qubits, right? So what is it? A qubit, similar to classical bit, can take similar values 0 and 1. It is represented in bracket notation. You might have all known this bracket notation already. So it is represented as ket 0 and ket 1. What is a ket 0? What is a ket 1? They are column vectors. So the quantum state of a system is represented, the mathematics of the quantum state is represented through this linear algebraic vector systems. It is different from classical bit in the property called superposition, where quantum mechanical laws allows the qubit to be in the superposition state of 0 and 1. All the distinct states of 0 and 1 can be visualized using block sphere of unit radius. So block sphere is our understanding of a single qubit system. 0, ket 0 and ket 1 are computational basis states. This is basic. So they are on the z axis of the block sphere. If you move 90 degrees from z-axis, uh, you go to Hadamard states plus and minus or plus I and minus I. So these are x basis states and y basis states. So a basic qubit, any quantum system is represented in terms of a vector called ket. So a basic representation is ket psi equal to alpha ket 0 plus beta ket 1, where alpha and beta are the probabilities. When you measure, you'll get either one output, either 0 or 1, with probability of alpha square or beta square. The whole probability should be equal to 1. So this is a very basic idea of quantum systems. Just as take it as a pictorial representation, it won't be happening in reality. So what happens is that, let's imagine this is an atom, this is an orbit states. So let us say the ring here is ket 0 and let us say the ring here is ket 1. So if you supply a photon of energy, if you supply a pulse of energy, the electron from here moves from ket 0 to ket 1 state. So this is the computation. We are literally computing on atoms. So ket 0 is represented as 1 0, ket 1 is represented as 0 1. So we already discussed some limitations that classical computers has. So how does a quantum computer addresses these limitations? Because of its properties, superposition is there, entanglement is there, parallelism will happen, massive parallelism is going to happen. Because the more qubits you involve, the more number of times you can iterate on a single stretch. Efficient simulation of quantum systems can happen. So yeah, this is the basic idea of the block sphere we are discussing. So this actually represent a single qubit state. So here is ket 0. It is the ground state. If you move 90 degrees in this direction, you go to plus. If you move 180 degrees from here, you go to minus state. Then on this equator, we have plus I state and minus I state. If you move 180 degree from ket 0, you'll get ket 1, which is a not gate operation kind of thing. So these are all the basic gates that we use in quantum computing. We know we have AND gates, NAND gates, NOR gates, XOR gates, XOR gates, etc. That basically create our computer architecture. Whereas similar to these gates in quantum systems, we have these gates: XZ, X gate, poly X, poly Y, poly Z, Hadamard gate. Hadamard gate is important because it creates a superposition of the states: phase gates, control gates, swap gates, etc. So all these gates exist. So let us take a small example. Let us start at gate 0. If I apply Hadamard gate, what happens? The qubit has to move to superposition state, which means it has moved to plus x, plus state, which is on the x side. Then if I apply Z gate is a phase gate. It induces a phase. So from plus, it has moved to minus. If I apply H gate again 90-degree rotation happens. It has moved to 1 gate. So this is a small example. So how do you physically realize quantum computers? Classical computers, we have universally same architecture all around. So you manufacture transistor, you manufacture VLSI devices, you put them. This has all happened. Then you attach memory and everything to it. So that architecture is same. But quantum devices, there are many physical realizations. We can create quantum devices to superconducting qubits. So they are called Josephson junctions. So recently, due to demonstrating that work in 2025, they got physicists got Nobel Prize. They demonstrated this idea only, Josephson junction idea only. Then there are trapped ion quantum computer, quantum dots are there, NMRs are there. So all these kind of different kind of methods are there to physically implement quantum computers. So this makes this stream more exciting because one, there are positives and negatives and everything, but there are hybrid architectures. You can create with photons, you can create with trapped ions, you can create with superconducting qubits, you can create Majorana bits, which Microsoft is working on. You can create with NMR also. All this is fundamental physics. So in all these kind of things, you can create quantum computers. But what are the obstacles? See, these systems are very, very, very sensitive because almost we are operating, we are working, we are playing with atoms. So these systems are very sensitive. They actually, scalability is the first issue. People are working on it, error correction bits are coming, logical bits are coming. So what happens is, if we want to improve it from 5 qubit to 10 qubit or 100 qubit or 1000 qubit, even very tiny noises will affect the quantum measurements. Qubits, initialization of qubits sometimes is also a challenge. Quantum gates that are faster than decoherence times, because when we are moving the qubits, they are not in stable states. They'll come back to their stable states again. Before they come back to their stable states, we have to take the measurements, we have to take the outputs, etc. So this decoherence times and everything is also an issue. Then we have to develop, sorry, then we have to develop universal gate sets of quantum computers and qubits that can be read easily. Sourcing parts for quantum computing is also sometimes technologically a challenge. We today, right now, almost we stand in NISQ era, 150 qubits, 100 qubits. People are moving to 1000 qubits and all. So we need error correction algorithms. We need more physical qubits. We need more logical qubits. So we right now stand in NISQ era, but when we move to 10,000 qubits or millions of qubits, we can really see the supremacy of this quantum computing. What are all the frameworks available? But I'm just introducing you. Qiskit's IBM framework is there. Circ by Google is there. Rigetti's Forest is there, and all. So these are some of the resources. So what we are doing is we have developed a quantum simulator in accordance with IIT Roorkee and IIC Bangalore. So this quantum simulator is a little bit different. It uses density matrix approach instead of state vectors approach. Yes, there are density matrix backends are there, but this was the first time in India density matrix approach is used. So I can show you the website. You can go to qctoolkit.in. So this is a website. You can log in. So what our Workbench, what does this provide? So how is this different? So here you can do syntax highlighting, you can do error checking, auto completing, These are all there. You can build and visualize quantum circuits like this. This is the code console here. You can introduce various noises here. So this is the website. So the quantum circuit will work here. So we can induce various errors in our kind of QSIM. We can introduce rotation errors, transitive selective pulse error, decay factor, decoherence, depolarization. All this can be easily calculated using a density matrix based approach. What is a density matrix based approach? I'll explain it to you in a moment. So this is all bell depolarization factor, all this. If you go to the website and on the right side, you have all these noise parameters. Directly, if I change the values of noise parameters here, in the code, it will automatically change and we have to run it. So decay is there, decoherence, depolarization, thermal factor, bell depolarization is there, etc. Then we have different types of measurements, single qubit measurement, expectation measurement, ensemble measurement in different bases. Here also you see we have different options. Plot is there, show partition, GPU. And then for qubit initialization, instead of defining qubits, you can directly give it through a binary string. You can directly give a maximally mixed state. You can give a uniform superposition state. You can give a thermal state with a decay. So this is the whole UI. So this is how it is. If you want to build circuits here, so if you want to work on this, here are some examples. So there are some courses here, algorithms here. You can go and practice on this. So these things are there. So that is about our workbench here. So how we are running is we are running right now on two supercomputers, Paramshakti and Paramutkas. If you give the circuit and run it, you'll get simulation ideas. So these are the jobs that we have already done. I can just show you something. Let it load. So let us have a small idea on how density matrix is a different approach. See, as you know, a qubit is a ket 0 or ket 1. You can represent 0, 1 states, plus states, minus states, which we have discussed already. Then this is the vector notations. Ket 0 is 1, 0, ket 1 is 0, 1, plus is 1 by root 2, 1, 1, minus is 1 by root 2, 1, minus 1. So this is all the states. So these are all the matrix of vector operations that happens on our quantum system, on our qubits. So we have complex conjugate operations. So ket psi is a vector, it is called ket. Bra psi, this is bra. So it is dual of ket psi, which is complex conjugate. Then for an inner product, you need to have a bra psi and a ket psi. So this will give you a scalar value. Then we have tensor product. Tensor product means if you have multiple quantum systems and you want to work on it, the representation will happen in a tensor product kind of structure. Then this is abbreviation for tensor product, conjugates, transpose, and unitary matrices, etc. So let's see. So how do you represent the same quantum system in a density matrix notation is we call this as outer product. Let us say this is rho naught, 0 and 0, which means ket and then a bra 1 0 1 0. So we'll get a matrix, a 2 by 2 matrix. So for a single system, for a single quantum system, you'll get a 2 by 2 matrix. So for 1 1, this is a state. So for plus plus, this is a simple matrix multiplication, column vector into row vector multiplication. Why are we moving from state vector into density matrices? For state vectors work perfectly on a closed quantum systems, which means there's no disturbance. An ideal case state vector will completely represent the quantum state. But as at the moment when the quantum system tries to interact with the environment, around, decay starts to happen, noise effects will come into picture. All this can be easily described in terms of density matrix notation. So the density matrix will give you the real assessment of what is happening to a quantum system in an open system case. Also, if you want to represent multiple mixed quantum states, density matrix notation works perfectly fine. So this is how it is. So kit place and bra place will be this one, 1 by 2, 1, 1, 1, 1, and 1 by 2, 1 minus 1, 1 minus 1. So our quantum simulator QSIM will give the output results in the density matrix notation. Quantum gates are unitary operations that operate on arbitrary quantum state psi and moves it to a new quantum state phi. So unitary operation is application of a quantum gate. In simple terms, to a new position in the block sphere for a single qubit system. Some of the quantum gates and their operations are as follows. You know X gate. So this is a poly X gate. So X gate turns the system from ket0 to ket1 and from ket1 to ket0. So here it is. If you apply X gate on a basic quantum state ket0, what happens? The matrix multiplication. So this is the X unitary matrix. This is our ket0 state. So the multiplication flips the qubit. So from 1 0 it becomes 0 1, which is ket1. Same operation if you want to do in a density matrix notation. So this is how it is. Because in a density matrix, we are using kit and its dual bra. So for kit, one X gate is applied. For bra, X transpose, X conjugate is applied. So this side 0 1 1 0 and our input state, which is, so it can be clear here. So this is inner products. Yeah. So the state here is ket0 bra 0. So our multiplication on it, it will give 1 0 0 0. So this 1 0 0 0 2 by 2 2 cross 2 matrix is our ket0 state. This 1 1 matrix 0 0 0 1 is a ket1 state, ket plus state, ket minus state. We'll all get a 2 by 2 matrix representations. So what happens is, what is a unitary gate? All the operations mostly happens in a unitary gate, which is A dagger equal to A dagger A equal to I. So A equal to basically A inverse. So this kind of unitary operations happen, but this happens in an ideal condition. So this happens in an isolated systems and ideal conditions. In general conditions, when noise effects come into picture, density matrix makes more sense. So let us see. X gate applied on 0 will give you ket1. So because here we are using, so if we use only ket0, so applying X gate will suffice. X ket0 will give you ket1. But here we are using density matrix based approach. We are using ket0 and its dual as well. Simply it can be written like this. So if you want to apply your unitary gate here, so uh, it has to follow the mathematical rules. So it becomes, so if you want to apply a gate in this state, it has to become, so X gate applied on ket0 and on the dual of it, conjugate of it should be applied. So U rho U dagger. So this kind of operation will be happening here. So we'll try to solve it again here. See, so this is X state 0 1 1 0. This is the density matrix state and this is the conjugate. Because they are unitary, these two are same. So on this matrix multiplication, it has flipped to 0 0 0 1, which is from ket0 state, it has moved to, row 0, it has moved to row 1, which is 1 1. So like that, that's mathematics happens. So when I show you the demonstration, so this is how we receive the outputs. That is why I'm giving you a basic introduction here. Similarly with H-gate also, H-gate will put your state in uh, superposition of both states. And then a small idea on tensor products. So if you are using a multi-qubit system, for example, take a 2-qubit system. So how do you represent? These two are two individual separate systems. So uh, they follow this tensor product mathematics, which means the whole Hilbert space increases. Hilbert space increases with every qubit. So if my qubit is 0, it is represented as 1 0. If there is another qubit in the 0 state, if I want to operate on both of these systems, I write it in form of tensor product structure 0 0. That is, we can also write like this, which means 1 0 tensor 1 0. So this expands the Hilbert space. So this is my first system 1 into second system 1 0, first system 0 into second system 1 0, which is 1 0 0 0. So this is the fundamental representation of a 2-qubit system. So can you guess what happens for a 3-qubit system? So if I take 0 0 0, my Hilbert space has to expand. It has to exponentially increase. So 1 0 tensor 1 0 tensor, sorry, 1 0, which means 1 0 into 1 0 1 0 tensor 1 0. So 1 0 0 0 into tensor of 1 0. So this will expand your state to 1 1 0, and all the 7 zeros, everything individually multiplied by 1 0. So this will become a vector with 8 elements in it. Single vector, actually, a single column vector. So 1 0 0 4 5 6 7 8. So this is for a 3-qubit system. This is how my Hilbert space expand. So can you guess what happens in a density matrix notation? Simple. So I have to take 0 0 in ket 0 0 bra 0 0. So 1 0 0 0 and its transpose conjugate 1 0 0 0. So it will become a 4 by 4 matrix, 1 and all zeros. So this is for non-ideal case of non-ideal case of quantum systems. These elements, these non-diagonal elements, represents the coherence relations between the quantum systems. So that is where this density matrix approximation will come into more use. So we know how to create an entangled state, right? So what is an entangled state? Even though the two states are spatially apart, they can be described only using single equation. They behave as one. So for an entangled state, what should we do? We have to use H gate first, then a control NOT gate. So let us take this. So this is a system 0, 0, H gate, and then control NOT gate. So what happens in this kind of system is, so initially the state is in 0 0, the 2-qubit system. On the first system, I have applied Hadamard gate. So the first system will go into superposition 0 plus 1 by root 2 tensor 0. The second system I have not changed. See, so the tensor matrix will now become 0 0 plus 1 0 by root 2. This will give you, and second gate what I have applied is a control NOT gate. So in this control NOT gate, what happens when the system, when the control is 0, the target won't change, but when the control is 1, the target will flip. So final system becomes 0 0 plus 1 1 by root 2. So this is how you create an entangled state. So this is all the basic demo to understand the mathematics of it. Now, so what happens is, in this QC workbench, this you can also download on your system. So this can be also downloaded as a backend on your system to work in your own personal laptops. So right currently, so this is how the output will come. So the job ran on DM simulator, and this is in the density matrix, the outputs will come. So this is has run on Paramutkar system. But currently there are a small anomalies in this website. So I'll suggest you to go to the GitHub file, download it and see. It is GitHub Qiskit Akash. So this you can download. Please write it down. You can download and run on your laptops. So you can go to Terra Upgrade. The installation and everything is available here if you want to work on it. So create a virtual environment. And then if you are using a Windows system, you have to pre-install Rust installer. For Linux systems, directly you can install it on the command control line. So let us see how this simulator works. So this is my basic demo file. So this simulator is a density matrix simulator. It is a backend on the Qiskit ecosystem. So we have the Qiskit ecosystem is there, the whole circuit creation, the circuit diagram, the circuit graphs, everything is in Qiskit, but the outputs will come in density matrix. So we create everything similarly. See, we create quantum registers, we create classical registers, and then we create quantum circuits. Everything is similar. In the output, we choose backend as DM simulator. So here I have chosen already. So this is the backend we have developed. So let us take a very simple example of what happens for a single qubit X gate. So this is my quantum register. This is my classical register. We'll go with 1 qubit case. 1. See what happened here. I have created a quantum register, a single qubit classical register for measuring a measurement of output. I have applied X gate and I have applied measurement gate. Let us see what kind of result will come back. So our result is the density matrix 0001, which means our ket0 state has shifted into ket1 state. So outer product of 00 has become outer product of 11. Same thing, let us try using some Hadamard gate. So yes, you can see in the diagram Hadamard is there. So what happens? The density matrix will be in a superposition state. So 0.5, 0, 0, 0.5. This is our final output. Let us try to create a controlled C0 gate. What happens? Yes, our control not gate is here. So 0 is control, 1 is target. So what do you think? Because I have not given anything, will anything change or not? So what will be the output? Is it 00, 01, 10? Only control not gate I have applied. Let us see. The output density matrix is only 00 state. So this is the 00 state representation of a 2 qubit. You see the 4 by 4 matrix 1 0 0 0 0 0 0 0 0 0, all the things. Because 0, when control is 0, the target will not change. So if I use an X gate here, will it change or not? Yes? Let us see. Let us change the control to 1. So you see the control is changed to 1. So now the system is in, here it is in 0 0 state. After the application of X gate, it will become 1 0 state. On 1 0 state, I have applied control gate. So what should it become? 1 1. So 1 1 is the density matrix. On the last line, 1 should come. Let's see. See, all the rows are 0 and only the last element is 1. So 1 0 is converted to 1 1. So let us go with some more difficult example like teleportation. So you all know teleportation. Maybe yesterday or day before yesterday, you might have gone through this protocol. So this is mostly in science fictions, mostly in movies. Everything people say teleportation, teleportation in animations, etc. But this is the reality of nature. It happens at a micro nano scale. So, and we have developed an algorithm. Quantum scientists have developed some algorithms on quantum teleportation. So let us go through this. Let us understand it a bit in detail. So what is the basic understanding of this teleportation is? Let us actually try to derive this. So it begins with this fact that Alice need to transmit an arbitrary state psi. So some random qubit. She doesn't know the state of the qubit. For this, Alice and Bob take help of the third party. So what happens in this state is an entangled state is created. One is shared with Alice and one is shared with Bob. So Alice, the random qubit Alice has, she tries to join that qubit with the entangled qubit she has. So according to entanglement, what happens? The qubit at the Bob side will automatically change. So when Bob tries to measure it, he'll know the exact output. So so there is no chance of somebody interpreting in between there. Yes. So this is a beautiful basic introduction. Let us see. So just now we got here how to create entanglement. A bell pair we have just now learned. So the same bell pair is created. So a bell pair is created. Let A be Alice and B be Bob. So Alice and Bob each one possess one of the entangled pair, which means if Alice gets this 0, Bob gets this 0. If Alice gets this one, Bob gets this one. So it's 0 0 or 1. So then Alice has a qubit state with her, right? So she has a random qubit, some sort of information which Alice thought it is meaningful. So that sort of information without anyone tracking, she can send. So we also know what happened with the tensor product. So on this system, if we tensor product Alice thing, so for clarity, let us derive it actually. So we have successfully created a bell pair. It is 0 0 plus 1 1 by root. Yes. So what happens is one is Alice, one is Bob plus Alice and Bob. But Alice wants to send this some arbitrary information, alpha ket 0 plus beta ket 1 to Bob. So how can she send? She has to somehow pair her set of information with the entangled qubit she has. So the whole system becomes, now Alice has two qubits. One is entangled pair and one is a information she wants to send. This is 1 and tensor with, let us see, 0 0 plus 1 1 by 4. So alpha gets 0 and pair with 0 0 plus 1 1. Here also 0 0 plus 1 1 by root 2. So in the next step, what happens? So this is the whole system. The qubit and the entangled pair will form the new system. So this pair will now become alpha 0 0 0 plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1. Sorry, 1 1 1 by root 2. Yes, see. Then what happens is Alice has to apply C naught gate on her two qubits followed by a Hadamard gate on the first qubit. So the result will be, so first Hadamard gate is applied, then C naught gate is applied. So Hadamard gate on the first qubit. Yeah, first C naught gate on her two qubits, control and target, then Hadamard gate on the first qubit. So this is how the state goes. So after this expansion, it will be 0 0 0 0 0 1 1 0 0 1 1 1, and this minus states will pop up. Finally, with small arrangements, if you have to separate them, then so this rearrange these states. So exclude the first two qubits outside and pair this with the last qubit. So what happens? Alice will have, if Alice measures something, she'll have the output at her side will be either 0 0, 0 1, 1 0, 1 1. So after this measurement, this two classical outputs she has to send to Bob. Then with the Bob measurement, the Bob side output will pop up to be alpha 0 plus beta 1, alpha 1 plus beta 0, depending on what the output is. So if Alice sends 0 0, the Bob measures it. No measurement will happen from the Bob side. So the output automatically will be alpha 0 plus beta 1. If it is 0 1, some X gate is applied, then XZ is applied, then ZZ is applied. So this kind of things will happen. So let us try to see the same thing in the density matrix simulator. So the algorithm we know. So we are initializing everything. We have created a 3-qubit quantum register, 2-qubit classical register, and a teleportation circuit is defined. So this code is basically available in older versions of Qiskit GitHub file. So it can be downloaded from there and you can change your backend and run on it after installations. So the first thing is we have to create a bell pair. So this function will create the bell pair. Then we have to define our side of gates. So this is the bell pair, right? Hadamard plus control not gate. It will create 0 0 plus 1 1 by root 2. And then Alice has to apply C naught gate to Q1 controlled by psi. So that kind of application will happen here. So this is the arbitrary qubit that Alice has. So it has to apply the C naught gate here, then the Hadamard gate. Next, the measurement operation will take place from the Alice side. Let's see, that is how the algorithm goes. So yes, the measurement operation from the Alice side. After measurement, so this is the four outputs will pop up 0 0, 0 1, 1 0, 1 1. So If 00 is the output, and if Alice sends 00 to Bob, Bob will do nothing. The measurement itself gives you the quantum information, alpha 0 plus beta 1. If 01 is the output, then he has to apply X gate. 10 is the output, Z gate, then 11 ZX gates. So, uh, sorry. So this transfer of information is purely classical. So you'll get some doubts. So if something is happening beyond the speed of light, if they're spatially apart and they're changing instantaneously, but here is a catch. Until you measure it, you don't know what it is. Yes or no? So Alice has to send 00011011 through classical channel. So the classical channel always respects the relativity theory and nothing can go faster than speed of light. So after the information shared through classical channel, the measurement happens at the Bob set, then only we'll get to know the output. So it is not violating any laws of physics. So yeah, this is the whole setup. So after measuring, this information has to be sent to Bob, and Bob measures it depending on the required output 00011011. So this is how it is. So we can test it using a random vector. Let us see, I have taken a random state vector and its a representation on the block sphere. So let us see. Somewhere it is more near to 0. It is almost 85% 0 and only 10 to 15% 1. So in our density matrix simulator, all the things have happened. See, here we have induced the random vector. So random information, some random information, not only alpha 0 plus beta 1, some kind of random state vector is there. Then all the algorithm happen, all the protocols happen. Finally, our answer will be this. So 0 in 87%, 1 is 12%. So although the output will not come in state vector, this is the same output because you can see it from the block sphere here. See, because it is almost 87% it is on state 0 and only 10 to 12% it is on state 1. The same output is used when we use the backend as our DM simulator. Here, see, we have used the backend DM simulator, and if you are running it, the probability output popped up as follows: 87% of 0 and 1%. So the channel, the information is transferred successfully. So what happens is there is a small limitation in DM simulator. Basically, the state vector simulator, it escalates in terms of 2 power n for every Hilbert space, for every new qubit. So if there are 2 qubits are there, you have a 4-dimension space, 3 qubits, 8-dimension space, 1 cross 8 column vector. But what happens in DM simulator is we are doubling it up. We are using the matrices. This will scale in power of 2 power 2n or 4 power n. So when doing half of the qubits, the memory will double up actually. So if I use 8 qubits, if the memory is 100 GB, for 9th qubit it will be 200 GB or something. So this kind of memory issues are there with DM simulator. But what happens is the main benefit of this kind of simulator is you can induce noise as you go. So as I have shown you in the website, these noise parameters are there. Everything you can go, you can run and verify your results and develop your algorithms on this. So this is the demonstration of QSIM. I hope it is interesting. I hope it is, I made it easy. Yep. Thank you. Any doubts? You can go on and register on the websites. Maybe it will work in this week or next week. There are some repairs going in the communication between supercomputer and the website. So it might get repaired. So you can go on website, check out the examples. There are courses are there, examples are there, quantum adders, subtractors are there. All kind of setup is there. And also in YouTube, if you have to go to CDAC Hyderabad channel, for all the examples, there are videos are there. A set of quantum courses there which we have conducted in last May 2025. You can also go through that for your basic introduction into quantum computing. Thank you.
It was such an insightful beginning to day 4, sir. Thank you so much for your time, expertise, and all the knowledge you gave all of us. This morning we had the absolute privilege of learning from Mr. Abhijith Tej, sir, who not only carries immense expertise in the field of quantum, but also holds a special connection to us as a proud alumnus of RGKT Basar. He began by laying down the future, foundation of quantum computing, helping us understand what truly makes it different from classical computing. He beautifully connected the dots between quantum mechanic principles like superposition, entanglement, and tunneling, showing how the same mysteries that govern nature also drive the power of quantum computing. And it was very nice that he walked us through the brief history of quantum computing, reminding us that since nature itself operates in a quantum way, simulating it must also be done in a quantum way. We explored the fascinating world of qubits, their representation, bracket notation, block sphere visualization, and understood how quantum systems and quantum gates from the very building blocks of this quantum technology. And then came the part everyone has been awaiting for, the hands on session using Jupyter Lab on QSIM, where he demonstrated live implementations. We witnessed a creation of bell pairs, one of the purest demonstration of quantum entanglement, and got a glimpse into how these theoretical ideas take practical shape through code and visualization. And we are very glad that he even shared a GitHub repository so that all of us can continue exploring and experimenting beyond today's session. It was truly remarkable, sir. The clarity, the simplicity, and the passion with which he explained complex concepts made the entire session both deeply technical and wonderfully amazing. On behalf of everyone present here and on online also, and on behalf of the Qiskit Fall Fest organizing team, I extend my heartfelt gratitude to you, sir, for your valuable time, your deep insights, and for bringing such energy and clarity to our campus. It's not every day that we get to learn from someone who bridges excellence with empathy, and you truly made this session one to remember. Let us give a big round of applause for his patience, knowledge, and the insights he gave us today. Thank you so much, sir. And as a token of gratitude for all the wisdom you have shared with us and the time you have spent to take this guest lecture to a next level, we would very much love to offer you a little felicitation, sir. So, could you please come on to the dais? Yes. I'd like to request our Dean of Academics, Dr. Shivaramakrishna, sir, and our Dean of Student Welfare, Dr. Ravi Gedala, sir, all our respected faculty members, our guests, Dr. Gnanyala, sir, and Srinivas Pasupati, sir. Everyone, please come on to the dais to present an honor of admission, a little felicitation to our today's guest. was created to nurture top rural talent. Its mission: imagine a university that discovers brilliance in the hearts of rural India, offering world class engineering education at no cost. This is Rajiv Gandhi University of Knowledge Technologies, better known as RGUKT or APIIIT, where dreams from villages turn into realities of innovation. Established in 2008 by the government of Andhra Pradesh, RGUKT was created to nurture top rural talent. Its mission is to bridge the educational gap and empower deserving students through a unique integrated pathway to an engineering degree. Guided by a clear vision, RGKD strives to be a premier institution of learning and innovation. It aims to provide high quality education in science and technology, foster creativity, knowledge, and innovation, serve industry and society with skilled graduates, cultivate leadership, ethics, and entrepreneurship among students. RGKT campuses are fully residential, vibrant, and self contained. Students enjoy digital classrooms, advanced laboratories, a vast library, and Wi Fi enabled learning spaces. Beyond academics, the university promotes sports, arts, culture, and well being with hostels, dining halls, medical facilities, and recreation centers, ensuring a balanced student life. RGUKT follows a distinctive 6 years integrated BTech program beginning right after class 10. Students spend 2 years building a strong foundation in core subjects, followed by 4 years of specialized engineering. Admission is through the RGUKT Common Entrance Test, which identifies and nurtures promising rural talent. Today, RGUKT stands as a symbol of hope and excellence, a community of thousands of young minds shaping their future through knowledge, innovation, and service. It's not just a university, but a life changing opportunity, proving that where you come from will never limit how far you go. To learn more and begin your journey with RGUKT, visit www.rgukt.in and be a part of the vision that transforms talent into tomorrow's leaders. So the first session of day 4 is an absolute hit. And now as we move on with the day 4 schedule, we are truly fortunate to have with us Mr. Soumya Ranjan Swain, a visionary leader at the crossroads of quantum computing and Gen AI. And let me take the distinct honor and privilege to introduce our guest lecturer today's session. Mr. Swain is a senior tech leader, Gen AI, at the IBM Waxton Center of Excellence and also an esteemed IBM Quantum Ambassador with an illustrious career spanning over 17 years across some of the world's innovative organizations. His journey is nothing short of inspiring. He has previously contributed his expertise to Honda Cars, Mercedes Benz Research and Development, Dell Technologies, and LTI Mindtree, where he played pivotal roles in driving innovation across domains like AIML, generative AI, agentic AI, data science, and even quantum computing. His academic foundation is equally remarkable. He holds a BTech in Mechanical Engineering from NIT Jalandhar, a postgraduate program in AI, a machine learning from BITS Pilani, and a PGDM in Business Analytics from IMT Ghaziabad. And currently at IBM, he stands at the forefront of bridging advanced AI engineering with quantum technologies, turning groundbreaking theories into transformative real world applications. And today, he will be leading us through an enthralling session on quantum algorithms from basics to advanced, where we will get to explore how the future of computation is being shaped by the fusion of quantum mechanics and as well as artificial intelligence. So, ladies and gentlemen, it is indeed a great privilege to have him with us today. Please join me in extending a very warm and enthusiastic welcome to Mr. Soumya Ranjan Swain as we invite him onto the dais with a big round of applause.
Can I speak now? Can I start? Yeah. Yeah. Okay. Thank you. Hello. Good morning, everyone. It's amazing to be here in Rgukt, this Qiskit festival. And first of all, I would like to thank all the student coordinators, organizers, faculty members, and my dear students who have come from others outsides and from the campus also for making this event great and happen today. So I'm Somiranjan Swai, and thanks, ma'am, for the nice introduction. Right now, I'm working as a senior technical leader in IBM Watson X Center of Excellence. Also, I'm a IBM Quantum Ambassador. So today's session, I'm going to talk about basics of quantum computing. Basically, it would be a refresher, as well as quantum algorithms. And basically, it will be a mix of, a little bit of theory, intuition, a little bit of mathematics, and Qiskit hands-on at the end. So in the interest of time, okay, so in the interest of time, I would uh, like to start with basic refresher. So just give me a hands up whether you are able to see my screen or not. Okay, thank you. So this is what I'm going to cover today. Uh, a quick refresher of quantum computing. I will just start from scratch. What is quantum computing? I know most of you must be knowing about bits, qubits, everything, but I will just touch upon those. I'll just go through quickly so that it will be a refresher for all of you before I start the quantum algorithm. So then I will go with quantum algorithms, a historical perspective. I'll be covering different types of algorithms, but basically mostly I'll be covering Deutsch algorithm, Deutsch-Jozsa algorithm, and Grover algorithm because these are the most foundational algorithms related to all other quantum algorithms. And then a little bit of mathematical deep dive, how it works, how to build the circuits in Deutsch algorithm, and then a Qiskit demo. So to start with, this is just a quick refresher of what is qubit. I would like to know who can define what qubit is. Can someone tell? Do you, can you give some mic or something? Yeah, what is a qubit? I would like to know. Can someone answer from the students?
Hello. Generally, qubit is an quantum information. Like, to be honest, it is a state, sir, which can be 0 and 1 at the same time.
Okay, so how is it different from bit?
Like, when it comes to the bit, it is a value. So, 0 is a value, 1 is a value. And when it comes to the qubit, it is a state, which can be 0, 1, and 0, 1 at the same time.
Okay, great. So yeah, that is basically the foundation of qubit. So when you talk about quantum computing, let me go to the very basic roots of how it all started. It started from quantum mechanics. It started from the dual nature of lights. So long back in early 1800s, there was a scientist called Young. He did the double slit experiment, and he found out that light is not only particle but also wave in nature. So it is popularly known as the Young's double slit experiment, which proved that light is basically both particle and wave in nature. So that is the main foundation for quantum computing. So later on, a lot of scientists work on quantum mechanics, and they came up with this idea of quantum computing, looking at the particle nature of both light and electrons, protons, these subatomic particles. Why can't we use their properties to compute something faster and get better results? So that is the basic foundation of quantum computing. So to start with quantum computing, let me just go to the classical system. We all are dealing with classical systems. Everything is classical in our surroundings, right? The laptop I'm holding, the supercomputer that is computing your chat GPT interactions, large language models, everything is classical. They are working on bits like 0 and 1, right? So, but in quantum computing, the ambience is totally different. The classical physics rules doesn't apply here, right? So, to have a foundation on that, so everything that we see can be termed as a system, and the systems have some definite states, right? So, for example, you are tossing a coin. It has two states, head and tail. You are throwing a die. It has six states, 1, 2, 3, 4, 5, 6. Probabilistically, you can call them as the sample space, right? This is nothing but equal to sample. The fan is rotating. So it has five states, for example, 1, 2, 3, 4, 5. So all these things can be defined as a system with deterministic or deterministic classical states, right? So there is something called probabilistic state. What if I say that the fan is rotating 75% high and 25% at low stage? That is where quantum computing concepts come in, right? So that probabilistic state can be defined like this. Let us say in our classical bits, which is 0 or 1, head or tail, let me define that 0 state is 75% of the time, that is 3 by 4, and state 1 is 1/4 of the time, 25% of the time. So I can denote it in a mathematical manner in a vector 3 by 4, 1 by 4. Okay. So this is how you define a probabilistic state. Unless you observe, suppose the uh, coin is spinning, right? Suppose you are touching the coin, it is spinning, and you have not seen it. Or even if you see it, you will not figure out whether it is head or tail, right? It is then only when you see it. That is when you measure it or observe it. There is a very important term, just remember it. I'll come it to the later in quantum algorithms also. When you see it, then you define, okay, it is head or tail. But unless you see it, you cannot figure out. It could be head or tail, right? So similar concepts can be applied to everything. Similar concepts can be applied to some experiments, like long back in quantum mechanics history. Schrödinger, he did a experiment with a cat. He put a cat in the box, and he released some gas. Okay. Then he asked somebody whether the cat is alive or dead. Then his friend said, "How would I know the cat is alive or dead unless I see it?" That is exactly what I want to point out. Schrödinger said, right? So unless you observe or see or measure, you cannot define what state the object or the system is in. Okay. When you open the door of the box, the cat might be alive or might be dead because of the gas. But unless you see it, it is in both the states. That is what quantum superposition is. Okay. So that is what qubit is. Mathematically, we define qubit in both the states with probabilities, right? So with certain probabilities, it is in 0 state, and with certain probabilities, it is in 1 state. Taking advantage of that superposition or probabilistic state, every other quantum algorithm is founded, and that is where we are heading for quantum computing. Everything is based on this superposition and something else called interference and entanglement that we'll cover quickly. So everything is clear? Are any questions? Okay, let me move ahead. I'll just quickly skim through the notations and the important terminologies that will be used for the quantum algorithm. So there is a ket notation. Okay, so 0 or 1, these are the basic qubits, right? So 0, when you say 0, you write it like this. I'm not sure. Okay, sorry. So what I was saying is that how to denote these qubits, right? So 0, we define it as 1, 0, and 1, we define as 0 and 1. So this is read as ket 0 and ket 1. So any qubit can be defined in these two bases, right? So for example, this 3 by 4, 1 by 4, this is a qubit. We can write it in the form of 0 and 1 basis states like this, okay? And then there is the bra notation. This is the opposite. This is the row form of ket. So ket 0 is 1 0 in a vector form, and then bra 0 is 1 0 in a row form. Okay. And then you combine bracket. That is nothing but the inner product. You write it like this: ket 0 and bra 0 bracket 1 0 1 0. That is 1. Okay. So these are the basics. Then how do you define this tossing of the coin in quantum notation? So let us say 50% of the time it is heads, 50% of the time it is tails. So you can write half half, half of the time it's heads, and half of the time it's tails. Like this, you can denote. And then this is the general notation. You can write any qubit. This is a qubit psi. You can write it in this form with 0 and 1. Okay. And this alpha and beta are the complex numbers. You take the modular of that and add it to alpha square plus beta square. It will give you the probability of 1. Okay. So this is the rule. These are alpha and beta are complex numbers. Mod alpha square plus mod beta square equal to 1. So the probability of finding that particular qubit psi in the state of 0 is alpha square and beta square. For example, if I write psi equal to 0.80 and 0.61, in general, I write it like this. So the probability of finding a 0 in this qubit is 0.8 square, that is 64%, and then finding 1 is 36%. And these are two very important terminologies. Please try to remember. That is why I have marked it in the square box. This is called Hadamard basis. We denoted it by plus and minus. So plus is nothing but 1 by root 2 0 plus 1 by root 2 1. Similarly, minus is this 1 by root 2 0 minus 1 by root 2 minus 1. So these two particular expressions will be frequently used in quantum algorithms. And these are the difference between bits and qubits. So I'll just skip through that. And what is the difference between gates, classical computing gates and quantum computing gates? So classical computing, the gates are not reversible, but quantum computing gates are reversible. Quantum computing gates can be denoted by matrix notation. For example, there is a gate called poly-X gate. So this is similar or the counterpart of NOT gate in classical computing. So this is denoted by X and this matrix 0, 1, 1, 0. If you multiply it with 0, it will give you 1. You can do the math yourself. So similarly, if you apply it to 1, it will give you 0. And this is the AND gate. This operation is irreversible, but here in quantum computing, the operation is reversible. Okay. So you can find out the inputs from the outputs in quantum computing because all the gates in quantum computing are reversible. And this is how you represent, bits or qubits in geometrical notation. We call it clock sphere. So basically, X, Y, Z. Y axis and Z axis is the 0 and 1 you represent, and then other qubits depending on the probability amplitudes, you space it around the globe. So poly XYZ gets like this. If I apply sigma X, that is the poly X gate, basically the NOT gate to 0, you will get 1. So earlier, so if this is my 0 vector or 0 state, if I apply X, it will reverse it. It will reverse it down towards the 1 state. This is how it is represented in block sphere. So similarly, other gates are there, X, Y, Z gates. So these are the matrix notations of each of these gates. So similarly, Z gate, applies a negative phase to the qubits. So your 0, 1 state will become 0, minus 1 state. That is what it is doing. Similarly, Y gate is there. And the most important gate for quantum algorithms is the the Hadamard gate. So just remember this slide, it's very important. When you Hadamard gate is represented by this matrix 1 by root 2, 1, 1, 1 minus 1, 1 minus 1. Okay. So when you apply Hadamard gate to 0 state, it produces this. This is 1 by root 2 0 plus 1. This is nothing but the plus state. Okay, we denote 1 by root 2 0 plus 1 as plus state. This one. Okay, so you get this Hadamard state, you get this plus state, sorry, you get the plus state, this one, this is called plus state. When you apply Hadamard gate to 0. And the interesting part is when you apply the Hadamard again to that, to this output, you again get back 0. Okay, so what I'm doing, I am applying Hadamard gate to 0. I'm getting this. Again, I'm applying another Hadamard gate here to this, and the result would be 0. This is going to be used in the algorithms that I am going to show you. So just remember, plus state is 1 by root 2, 0 plus 1. Minus state is 1 by root 2, 0 minus 1. And when you apply Hadamard gate to 0, you get the plus state. Again, you apply another Hadamard gate, you get the state 0 back. Okay. Similarly, if you apply Hadamard gate to minus state, you get 1 back. So this is the basic what you must remember for quantum algorithms. Okay, quantum circuit is nothing but the combination of various qubits and gates. So this is how you denote it. You supply qubit, and this is the S gate, H gate. You write it. This means that qubit is going through the X gate first, and then the Hadamard gate first. And this is the math, which so you can see you write it like this QXH, but when you do the matrix multiplication, it is the reverse. Okay, so you write QXH, but while doing the matrix multiplication, first you write H matrix, then X matrix, then the qubit. Okay, so H sigma X, if you multiply this, you will get this one. Now I am going to apply, if my Q is 0, H sigma is 0, you will get minus, which is nothing but 1 by root 2, 0 minus 1. Okay, so this is the basic notation of gates and matrix representation of the qubits. And in Qiskit, you might have seen, this is how we are going to do the building of the circuits. We'll define Q, X gate, H gate. Then this is the measurement. When you measure, you'll find one result, 0 or 1 with certain probabilities, right? So this is how you are going to build the circuits. Okay. Now coming to the main part, quantum algorithms. So before I start with quantum algorithms, can someone tell what algorithm is? What is an algorithm? Anyone? Sorry.
Algorithm is a step-by-step process, starting stage to ending stage.
Yes. Yeah, you are absolutely right. So algorithm is nothing but a set of instructions in plain language, simple language. That is mathematical term algorithm, but it's a step-by-step procedure to perform a task or to solve a complex problem. We define a set of rules or set of instructions to solve this. Okay, so that is what algorithm is. Then next question is, what is quantum algorithm? Quantum algorithm is nothing but a algorithm or a set of rules or a set of instructions which uses the principles of quantum mechanics. But now the question is, what is the purpose of studying the quantum algorithms? Why? Because we are dealing with a lot of algorithms in everyday life, right? We are all now AI or data science, machine learning, chat GPT, large language models, LLMs, agents. These are all our daily part and parcel of life. They have become the part of life now, and they are nothing but algorithms, right? Then why quantum algorithms? Are not they enough? Then why do we need to study quantum algorithms? So the simple answer is quantum algorithms, as I said, it uses the principles of quantum mechanics. But why? I'll come to that. Why should we study quantum algorithms at all? So when quantum computing started, it started maybe in the late 1980s or early 1990s. That time people were not looking for solving practical use cases. Even at that time, the classical computers were not that faster, or they are not that computationally, sophisticated to solve the way they are solving right now. Imagine uh, running the chat GPT model, large language model on a computer 15 years back. I'm damn sure it will not have produced the same result that you are getting. Right now, you are just writing it and it is producing the results because of the advance in computational technology like GPUs. We have accelerated GPUs, TPUs, everything. But early 90s or the late 1980s, people are not looking for solving, real problems with quantum computing. They were just looking for certain problem statements. How to prove that quantum computing logic is faster than the classic computing logic? Okay. So that led to the development of various quantum algorithms. So one such scientist was Deutsch. So in 1992, he showed that quantum computing logic is faster than classical computer logic. Okay, so that is called the Deutsch algorithm. It doesn't have any practical application as such, but this is the foundational algorithm or the foundational step towards the sophisticated quantum algorithms such as Grover's algorithm or Shor's algorithm and other. The modern algorithms like VQA and uh, uh, you know variational quantum eigenvector algorithms. These are all sophisticated algorithms, but Deutsch algorithm is the basic foundational algorithm which gave rise to all these algorithms. Okay, so to simplify the process, how do you measure the performance of computing systems? Okay, so to measure the performance of computing systems, there are 3-4 parameters. Whether your computing system is computationally fast, whether it is calculating or doing the computations very fast or not. That is one metric. Second metric is how much space or memory it is occupying while doing the calculation, right? So let us say ChatGPT is occupying 2 TBs of data on the GPUs. It's not good, right? So that is one metric to measure the performance of computing algorithms or computing systems. Similarly, query complexity. How many calls you are making to the computing system and how fast it is returning the answer. That is also how you measure computing performance. So this is the history of quantum algorithms. As I said, 1992, Deutsch came up with that simple algorithm to prove that quantum computing is faster than classical computing. Then the extension come, Deutsch and Jozsa, two scientists, they came up with the Deutsch-Jozsa algorithm. Then 1992, again towards the later part, Bernstein Vajirani, this algorithm came. Then Simon, then Shor's algorithm. Shor's algorithm is very useful. It is used in cryptography. Basically, factor out big prime numbers, which was not or which is not possible at all with classic computers. Then came in 1996 Grover's algorithm, which is a search algorithm. You search unsorted database quickly, and Grover showed the practical use case of quantum algorithms. Okay. Then we have sophisticated algorithms, as I said, VQE, QAOA, and then one big thing IBM did in 2016. IBM made the quantum computers available on the cloud. So right now anybody can access quantum computers, but with limited, depending on the subscription. But you can also run the programs on the quantum computers. Then we have other sophisticated algorithms like pricing option. All these use cases came later. So as I said, Deutsch algorithm is the basic algorithm and the foundational algorithm for all the quantum algorithms. So what is it exactly? Any idea who already knows what Deutsch algorithm is? Does anyone know what Deutsch algorithm does? Okay, I'll tell you in simple language. So let us say you have a magic box, okay? In quantum terms, we call it oracle, or let us say it is a black box, a magic box. Okay, it gives certain inputs. It gives an input. It takes an input, gives an input, output. Right. For example, this is my oracle or the magic box. Mathematically, it is a function, right? So let us say it is a function, black box function. If it is takes 0, gives 0, takes 1, gives 0, then we call it a constant function, right? Or it takes 0, gives 1, takes 1, takes 1, gives again 1. So no matter what you give it, it gets you constant output. That is called constant function. Similarly, there is another function, another black box called balanced function. Now, when it takes 0, gives 1, takes 1, gives 0, right? So the outputs are not same. That is why it is called balance function. But let us say you are given this function or the black box, and you are given, let us say, two inputs, two zeros or two ones or 0 or 1. Now you want to find out whether this output, whether this function, this black box is constant or balanced. What would you do? How would you do that? So what would you do? Typically you will put 0, see the output is 0, right? So that is one call or one query. Similarly, you put 1 again, you then check whether it is coming 0 or 1. So earlier you got 0, now it is coming 0. Then you determine, okay, it is a constant function. But now you are giving 0, getting 0, one call or one query. Again, you are putting 1, but you are getting 1. Earlier you had gotten 0, now you are getting 1. Then you determine or decide that, okay, no, this is not a constant function, this is a balanced function. But to determine this constant or balanced function, you used two calls or two queries, right? You queried twice this black box. Imagine, let us say there were 16 such numbers, okay? To check whether the function is constant or balanced, what would you do? You will put one queries each time, 16 times, and 16 times you will note the outputs, and you check 16 times if it is 0 or 16 times it is 1, then it is constant, right? Or similarly, half of the outputs are 0 or half of the outputs are 1, then you determine it is a balance function. But to do that, you had to query 16 times, right? Similarly, 16 is a small number, 2 is a small number as shown in the figure. Similarly, let us say you had 1 million or 1 billion inputs like 0 or 1s. Then you have to query 0 or 1s 1 billion times, right? What if I say this Joyce algorithm, it promises just with one call, one query, you will figure out whether it is a constant or a balance function. So you give all the inputs once, apply Deutsch algorithm, you get to know whether it is a constant or balanced function, whether all the outputs will be all zeros, all ones, or half of them will be zeros or half of the ones. Okay, so that is the essence of Deutsch algorithm. So that is what I have defined here. F0 equal to F1, then F is constant. F0, F1 is not equal, then F is balanced. So classical computers need two queries of the function to check whether the output is coming balanced or constant. So if you define in terms of n, it will be 2 to the power n minus 1 plus 1. So if you have n strings, n inputs, at least you have to try 2 to the power n minus 1 plus 1 times. Okay. So if you have 16 inputs, at least you have to try 16's half is 8. 8 times you try, you check zeros. Still you have to try one more time. That means 9 times. At least to check whether the next output is 1 or 0. Then only you will be certain, okay, all the functions will be zeros or ones, or half of them will be 0 or 1. So in mathematical terms, it is 2 to the power n minus 1 plus 1. But the Deutsch algorithm promises that with just one call, you will be able to determine whether all my outputs are going to be zeros or ones, whether it is going to be constant or a balance function. So how do you do that? To do that, we define the oracle like this. Okay, oracle means I'm defining it as a UF, as a gate. Basically, it's a quantum gate. Two qubits will be going as input, X and Y, and the outputs will be, the first qubit will be remaining same. The second qubit would be defined like this: Y XOR f of x. Okay, so this is the typical output. This is the oracle. Okay, so this Y XOR f of x is nothing but Ajay is you might be knowing, this is the C naught gate. This same as XOR gate of classical computing. Okay, so remember this formula. This will be useful in the deriving the algorithm. So I apply x and y, two inputs. I can write them as x into y. So this is nothing but your, we call it cross product of the qubits. So x, y inputs can be defined as, can be written as x, y. Then I'm applying this oracle UF, and then I'm getting x, y plus fx. So remember this one. Now, just to show how it works, now I put y equal to 0. What will happen? So if x is something, I'm giving y equal to 0. The output will be x, y is 0, XOR f of x, 0, XOR f of x is nothing but the function itself, the output itself. So x plus 0 plus something, 0 plus 0 XOR something is nothing but the bit itself, x fx. Okay. Now, you remember this minus Hadamard minus state I had told you, it will be useful in Deutsch algorithm. 1 by root 2 0 minus 1. So now what Deutsch algorithm does, it replaces this y with this minus state. So if I put minus state along with x state, what will happen? So this is the algorithm. This is the derivation. You apply the oracle to each of the qubit. You write it first like this: x, then minus state is 1 by root 2 0 minus 1. Then you do the multiplication, x take inside the parenthesis and all those things. And then this is where the oracle, this rule is applied. Okay, half x 0 plus fx. Finally, you will get 1 by root 2 x fx minus x complement of fx. If you go through this, I'll share the slides. You go through this step by step to get the clarity by yourself. So finally, you will get this expression. Now look at this expression: x into fx minus x into fx complement. Okay. Now, if fx equal to 0, that means we are trying to test whether it is constant function or balanced function. If fx equal to 0, you put fx here equal to 0 here, and fx bar will be 1. So if you do the little rearrangement, you will get back x minus x minus 1. Okay. So this is minus 1 to the power fx, x into minus. So this expression is very useful. It's called phase kickback, or we call it phase oracle. When in a normal oracle, you are imputing a minus state, you are getting this state, minus 1 to the power fx, x into minus 1. Okay. So this is called phase kickback. So the phase information is coming to the function itself. This is used in the derivation later. Now we know that if I put x and minus to the oracle, I'm getting back this expression. Now let us use this in the further algorithm to determine how it is going to determine whether it is constant or balanced function. So how to build the Deutsch algorithm? First, what you will do, there will be two qubits, 0. You input 0. Then you apply Hadamard gate. 0 to Hadamard gate, it will give you the plus state. Then 0 to X gate, that is the NOT gate. It will give you 1 here. Again, you apply Hadamard gate to the 1 qubit, it will get you the minus state. Okay. So while entering this oracle, here I am denoting all the states as psi1, psi2, psi3. Okay. So the psi0 state is 0, 0. Here, after you apply NOT gate, here now the psi1 state is 0. Because you applied NOT gate, it has become 1. So at psi1, this is 0, 1. I am not, I have skipped this. Here it will be 0, 1. Okay. Then you apply H or Hadamard gate to 0 and 1. So when you apply Hadamard gate to 0, you get plus state. When you apply Hadamard gate to 1, you get minus state. So that is what psi2 is indicating here. So to the oracle, the inputs are plus state and minus state. Okay. Now you get back psi3. You apply that phase kickback I had written for your understanding. You can go through it. So you do all the calculation, rearrangements. I could not type it, so I wrote it down on the paper and printed it here for step-by-step explanation, because I don't think you'll find this explanation clearly step-by-step in any of the materials. So I just tried it myself for your understanding. So plus state is this, minus state is this, and you do all the associative rule, multiplication rule. Psi3, you finally get like this. You apply the phase kickback, you'll get back this equation. So at psi3, your state would be like this. Now the magic happens. How to determine whether it is constant or balanced function? What you do at psi3, here, the highlighted one, you apply again another Hadamard gate. Okay. I apply Hadamard gate to the highlighted one, this one, and I see the results, what is coming. So if I, okay. Now psi3, look at psi3. Psi3 is this. So I will consider two use cases when f0 equal to f1 equal to 0 or f0 equal to f1 equal to 1. That is our constant function. Similarly, another use case is f0 is not equal to 1. That is our balanced function. Okay. So when f0 equal to f1 equal to 0, I get this expression. You put just f0 and f1 equal to 0 here in this expression, you will get back this. And similarly, if you put f0 equal to f1 in psi3, you will get minus 1 by root 2, 0 plus 1. So psi3 is finally coming to be plus minus 1 by root 2, 0 plus 1, which is nothing but my plus state. So this is plus minus plus. Okay. So psi3 is now here, my state is plus state. Okay. Now, you remember when you apply Hadamard gate to plus state, you get back 0. When you apply Hadamard gate to minus state, you get back 1. So right now, what I'm saying is that after doing all these calculations, after doing oracle, here at psi3, my state is either plus or minus plus state. Okay. My state is plus, I'm applying Hadamard gate. I will get 0 state back. Okay. So if I get 0 here, I'll measure that as 0. That means, and which condition led it to 0? This condition. f0 equal to f1 equal to 0 or f0 equal to f1 equal to 1. Okay. This is the condition I applied and I got back 0 at the psi4 state. That means my function is constant. Okay. So in one query, I didn't do anything. I didn't check whether the first input is giving me 0 as output, the second input giving me as 0 or 1 as output. I didn't do two queries. I just put them together at one go, and using Deutsch algorithm, building these circuits, here I am getting that my output is coming to be 0 with these conditions. Okay. So this is nothing but the constant case. Okay. That means if I am measuring 0 at this position, it is a constant function. Similarly, if I measure 1 here, you do all the calculation. If psi4 is giving 1, it is a balanced function. Okay. So this is how Deutsch algorithm works. I know it'll take little time to understand properly, but this is the essence. This is how you build the Deutsch algorithm. In one go, you put all the inputs and just measure. If it is 0, if the measurement says that it is 0, it is a constant function. If it is a 1, it is a balanced function. That's it. Similarly, I'm just showing you 2 inputs. It can be extended to billions of inputs also. Okay, so that is the extension called Deutsch-Jose algorithm. So you put all the inputs together and measure. If all the inputs are giving 0 at the cipher stage, it is a constant function. And if it is giving 1 at the cipher stage, it is balanced function. So you can imagine how much speed up has happened over the classical logic, right? So how you build it? So it's very simple. Take 2 inputs, take 2 qubits, 0 and 1, apply Hadamard gate, apply the oracle, then again apply the Hadamard gate, you will get the Deutsch algorithm completed. It will give you whether it is 0 or 1. Okay, I'll show you in Qiskit also. Now comes the Deutsch-Jose algorithm. That is nothing but the extension. So in Deutsch algorithm, you are just giving 0 or 1 or 2 inputs. Now, what if I say there are billions of, I have already explained. So, and X could be not only 0 or 1, it could be a string. 0, 0, 0, 0, 0, 1, 0, 1, 0, like this. It could be a string of numbers. So how many inputs you get? For example, the extension Deutsch-Jose algorithm, the inputs would be strings like this 0, 0, 0, 0, 0, 1, like that, n numbers. If you are getting all zeros, then it is constant function. If you are getting all ones, again, it's a constant function. But if you are getting half of them as zeros, half of them as ones, then it is a balanced function. Same application, but the circuits will be changed. How the circuit will be changed? Only the upper person. In the Deutsch algorithm, the basic algorithm, you had only 1 0. Now what you will do? You will put n number of zeros as input. So that is denoted by like this. So 0 cross n. That means you have put n zeros into the oracle. And similarly, you have applied h cross n. That means you have applied n number of Hadamard gates to the zeros. Okay. And then again, you are applying Hadamard gate n times, and then you are measuring. Okay. So if you are measuring all zeros here, then it is constant function. If you are measuring all ones here, you are getting balanced function. This is how it is. This is the essence of Deutsch-Jose algorithm. And these are the derivation. You can go through it later. Just step by step, I have made it very clear to understand. So everything is same as the simple Deutsch case. 0 and only 2 strings, but it is just a extension like n steps, addition of n steps. So here, that is what I'm saying here. If you are measuring all zeros, then it is a constant function. If you are measuring all ones, then it's a balanced function. Okay, so before getting into the Grover's algorithm, I'll not take much time because it's already 1 hour. I'll just show you how to build the circuit in Qiskit. Okay. So Qiskit, you import all the things from Qiskit. Import star means import all the libraries. Then to show the plottings, you import matplotlib. I define a circuit. A circuit. I import quantum circuit 2 1. That means two classical inputs and one measurement. Sorry, 2 quantum inputs, qubits, and 1 measured state. Then, as I said, it's very simple. You have to take 2 inputs, 0, 1, apply Hadamard gate to both of them. That is what it is doing. So I'm taking 2 inputs, 0, 0. So by default, in Qiskit, it is Q0, Q1, both are zeros, okay? So to make it 1, you have to apply the NOT gate, X gate. So that is what it is doing. So I'm applying this 0, I'm applying Hadamard here, circuit.h0. Then I'm applying X gate to make it 1, then applying Hadamard gate here. x and 1. And then just for the barrier, I'm showing it as a state. This I'm writing circuit.barrier, and then I'm outputting the algorithm like this. Okay. And now the first part is done. Now coming to the oracle part, how to build the oracle here. This is the oracle. Okay, this is the UF notation that I saw. This is nothing but the C not. There is a gate called C not gate, controlled not gate. So if the 2 bits are 0 0, it will not change. But if the first bit, the control bit 1, then it will flip the sign. That is nothing but the oracle. So to build that oracle, I'm defining the oracle here. Cx equal to 0. This is the oracle, the control not gate, and applying to the first qubit 0 and 1, and the second qubit. And then again, this is the final Hadamard gate I'm applying here. Once I'm putting the oracle, then I am putting another Hadamard gate on the first circuit, first qubit, to get this. Okay. Now my Dodge circuit is complete. Now comes the measurement phase. Now I have to measure here, right? The psi4 state in the explanation. Here I'll put the measurement, and I'm done. Now I'll measure. If my measurement is giving 0 with 100% or 1 probability, then it is constant function. If it is giving 1, it is balance function. So very simple. Okay. So now you can see it's giving me one state as with I did all the computation, all the simulation. I have I have already used AR simulator here. I've used the AR simulator. This is the way you write it, and then you count how many times it is giving the output. So you can see the output is coming as 1. That means it's a balanced function. If it had come as 0, it would have been a constant function. So this means that I'm measuring 1 here. Okay. So here I am getting psi3 as the minus state. I'm applying Hadamard gate. I'm getting the 1 state, and I'm measuring that. So this is how you perform Deutsch algorithm, right? Similarly, as a homework, you can take extend it as Deutsch algorithm. You put more qubits, n number of qubits, take any number like 3 or 4, build that circuit and check. So if you're putting n equal to 3, 8 outcomes will be coming, and you will get 0 or 1 like this as the output. Okay. So this was all about Deutsch algorithm. Any questions? Any questions I'm asking?
So, so, so as you mentioned, Oracle is some sort of black box, right? Like we don't know what exactly happening in the inside. We just getting output either balanced or constant. So if we don't know what's happening inside, so how can we apply the same thing to the other necessity use cases that we're gonna get in the foreseeable future? Like what my doubt is, like in the black box, like we only get output for the required inputs. We are only getting the output. We don't know what exactly happening inside the black box or the oracle. So if I got a situation where I need to implement the oracle, how will I get to know about the functionality and the implementations that are happening inside the oracle?
Okay. So to answer you, okay, the assumption here is that Oracle knows the output. Okay. This is just a way to demonstrate the quantum logic is faster than the classical logic. But in the background, the Oracle knows, but we don't know that what the Oracle knows. Okay, this is how. For example, let us say in a computer you are putting passwords. Okay, let us say 1,000 combinations are there. Computer knows what is the password, but we don't know. So let us say you are a hacker. You want to hack my laptop. I have put a password. When you are entering the exact password in the back end, it is matching all the passwords. If the password matches, it is letting you log in. That is what the Oracle. Now the computer is Oracle. So in the back end, it knows, but we don't know that what it knows.
The
That
hashed,
is,
the
yeah,
hashed passwords, some other stuff
yes,
that you're
exactly.
referring to.
So as a classical setup, what I would do, I'll put, let us say, 1,000 combinations are there. As a hacker, I would put all sorts of combinations, 1, 2, 3, 4, all sorts of combinations to check whether I am able to hack this computer or not. So when I found that combination which exactly matches the password, then it will let me in, right? That is what the Oracle. Okay. So
Okay, sir.
I know this is a counterintuitive, but this is just to demonstrate that the quantum logics can be faster than the classical setup. That is what.
Okay,
So
sir.
the
Thank you.
Oracle knows, but we don't know what the Oracle knows.
Yes, I
This
get
is
it.
how I am going to put it. Okay.
Yes, sir.
Anything else? Okay, then I'll quickly go through one very useful algorithm. If time is there, just 5-10 minutes. Yeah. So there's a very useful algorithm, Grover's algorithm. That is also, Joyce algorithm is also kind of related to that. The concepts like phase kickback and all the other things. Um, it's very simple. If you look at in a simplistic manner, but mathematically it will definitely look very complex. So Grover's algorithm is nothing but what the problem is. This what you asked right now, what he asked. Let us say there are many passwords, and you want to find out which one matches. So find one marked item among n unsorted items, right? So let us say there are n items, and you have to query one each time, right? N times you have to query to find out the right match. That is what the essence of Grover's algorithm. So Grover's algorithm says instead of trying or experimenting for n times, you can do it root n times in the order of root n times. That is what the essence of Grover's algorithm is. Okay. So that is also quadratic speed up. So let me just show you one quick classic example. So simple example, let us say there is a list of numbers 5, 4, 6, 9, 1, 3, 7, 8, 9, right? I don't know which place this, I want to find one number, let us say number 8. Okay. So if right now I'm seeing the list, that's why I can directly tell it is at the last but one position. But if it is not there, what I have to do, I have to query sequentially. I have to